Today's warm-up question. Today's warm-up question says, John pulls a wagon with 20 newtons of force at 65 degrees above the ground. Amy pulls her wagon with 20 newtons of force at 35 degrees above the ground. If both wagons have equal mass, which will accelerate more? You'll notice when you read the question that both Amy and John are using the exact same amount of force, 20 newtons, and they're both pulling identical wagons. I know they don't look identical in the picture, but it's telling us in the question that they have equal mass. So we're going to assume that they're identical wagons. So the only difference here is the angle at which they are pulling these wagons. And you can see it illustrated in the picture. He's pulling at a steeper angle than she is. Okay, and so the question is, does that affect the acceleration? And the answer to that is yes, it does. Okay, when you pull at a steeper angle, then you're going to have a greater vertical component and a smaller horizontal one. So John is going to have a smaller horizontal component, whereas Amy is going to have a larger horizontal component and a smaller vertical one. So although they're using the same amount of force, only a portion of each of their forces is horizontal, and that's the portion that's responsible for the acceleration of the wagon. They're not lifting it off the ground, they're pulling it across the ground. And so the one that has a greater amount of horizontal force is going to have a greater horizontal net force and thus a greater acceleration. If you look at these angles here, without even doing any math, you can see what I was just talking about. You're welcome to do the math though, but you can see that this is smaller than this one. If you wanted to solve for this component, the x component, it would end up being 20 times the cosine of 65 degrees, which is 8.452. Whereas if you do the same thing with the values they gave us for Amy, this one's cosine of 35 degrees equals fx over 20, so it's 20 times cosine 35. You'll notice that she has almost twice the amount of force that's horizontal. So the net forces aren't the same because it's not a vertical net force we're looking at, it's just the horizontal. They have different amounts of horizontal force and thus they have different net forces, which of course means different accelerations. If you pull with more net force in the horizontal, you will get a greater acceleration. Okay, because the horizontal force is responsible for acceleration, the smaller the angle, the greater the amount of force in the direction of acceleration. Thus, the force at 35 degrees, that's Amy, will cause a greater acceleration of the wagon. So Amy is going to have more acceleration for her wagon compared to John. So that's the answer to today's warm-up if we're looking at, let me see what the wording was. Hold on. If we're looking at the wording, which will accelerate more, Amy's wagon will accelerate more. Okay, that's what you need to select in the warm-up. All right. As I said, we're going to do some more practice problems today that are similar to the ones that we were doing last week. We started an assignment last week on Friday. That assignment is due today, and there's not really anything new that I'm going to go over. We're just going to go over some more practice to hopefully get you more comfortable with these problems where you have forces applied at an angle. So this first one says, a crate with a mass of 31.0 kilograms is pulled over the floor with a diagonal force of 275 newtons. The force makes an angle of 24 degrees with the horizontal. Assuming there is 100 newtons of friction between the crate and the floor, find the acceleration of the crate. Okay, so they gave us quite a bit of information here, but the first thing you're going to want to do is draw a free body diagram. So instead of a box, I have a circle, same thing. We're just going to draw the forces acting on the crate, which is represented here by a black dot. Okay, I do know that I'm going to need to get the components of this diagonal force, so I know I'm going to have Ft in the x direction, okay, which the equation for that's right here. We're solving for this. It's adjacent to the angle, so I'm going to use cosine. That's the ka from SOHCAHTOA. Because I'm looking for the adjacent side, I have the hypotenuse and I have the angle. So this is the equation that you use to solve for it. Cosine of 24 degrees equals ftx divided by 275, which means in your calculator what you're actually typing is 275 times cosine of 24. Again, I would strongly encourage you to practice typing this into the same calculator that you plan to use on the test, okay, whenever we get there. Also, make sure you're in degree mode. If you enter this correctly into that calculator, you do get 251 newtons. That's rounded, but 251. We're going to do the same thing in the y direction, but for the y direction we're using sine because FTY is opposite the angle. So we're looking for opposite. We have hypotenuse, we have the angle. We can say that the sine of 24 degrees equals opposite FTY divided by 275, which again means that in your calculator you are typing 275 times sine 24. When you do that, you're going to get your vertical force, and please note it is upward. Again, this is at a diagonal, but it's a diagonal going up, so the forces are to the right and up. And when you type that in, you get 112 newtons. Again, I'm rounding them just to make my picture not look so cluttered. You should keep the decimals in the calculator screen for future calculations when you need it. All right, but those two vectors represent my tension. So I have a horizontal and vertical component, and that was one of the first steps. If you have a force at an angle, get the components. That means you're going to have to do some trig. All right, so we have our components. There are other forces here that we need to include. We have the force of friction, which is 100 newtons because it told us in the question. Okay, so I'm not just making it up. It said in the question 100 newtons of friction. Okay, we also need to include Fg. There's always gravity. In fact, we could have drawn this one first. Force of gravity acts on everything, including this crate, because it's on Earth. Now Fg, if I want to solve for it, we have an equation. Mass times gravitational acceleration, which on Earth is 9.8, or technically negative 9.8 because it's down. Okay, and so we would multiply the mass of the crate, which was 31 kilograms, by 9.8, and that would give us our force of gravity as 304 newtons, and it is down. If you want to put a negative in front of it, you can, but we're going to be drawing it on the picture next to a downward pointing arrow, so the direction will be indicated by the arrow. But you're welcome to also label it as a negative number there. So we have friction now. According to this diagram right now, I have unbalanced forces horizontally, which I should because it says he's accelerating it. That makes sense. But I also have unbalanced vertical forces, and that does not make sense because he's not lifting the crate off the ground and the crate's not falling. These arrows right now make it look like the crate's falling, okay, because there's a net force down, okay, and we don't have a crate that is accelerating downward. Instead, we need to include an additional upward force to balance our forces out. So what force am I missing that goes up? Normal force. That's the support from the floor. Okay, so we need normal force, and we need the normal force to add to 112 in order to get 304. We need the forces balanced. Okay, so there's not an equation for normal force. You're going to draw it according to your diagram. If my vertical forces need to balance, that means my total up force needs to equal my total down force. My total down force is 304. So 304 equals 112 plus Fn, and solve for Fn, okay, which is 192. So when you add these two together, 192 plus 112, you should get 304. Again, I'm rounding everything to whole numbers to keep my picture simple, but be aware that there are decimals on a lot of these. All right, that's all my forces. I now have vertical balanced forces and horizontal unbalanced forces, which is exactly what the question described. So we now need to find the net force acting on the crate. Okay, again, net force does need to be determined separately for vertical and horizontal motion. Vertically, I have zero net force. I drew it like that on purpose because the question does not describe vertical acceleration. I wanted it to be zero. I need it to be zero. But horizontally, I do have a net force. So we're going to solve for F net x. Okay, F net x is the sum of my horizontal forces. That's 251 plus negative 100. Again, when it's pointing left, please include that negative sign because that means we're really subtracting. So 251 minus 100 is 151 newtons to the right, and that is my net force. It's my total net force as well because there isn't a vertical one, but it is my horizontal net force. All right, so we have our horizontal net force. Our next job is to calculate the acceleration of the crate. Again, I can find acceleration using F net equals ma. I know F net, 151. I know the mass, it was in the question, 31. The acceleration will happen due to that net force acting on that mass using F net equals ma. And so this is my substitution step. F net, 151, equals 31 times a. If I want to solve for A, I'm going to divide both sides by 31. 151 divided by 31 gives me an acceleration of 4.9 meters per second squared to the right. Okay, so again, if there's a force at an angle, we just went through yet another example. And what we're doing is starting by getting components of diagonal forces, figure out how much is horizontal, how much is vertical, and then draw all of those on the free body diagram along with things like gravity and friction and normal force or whatever else. Any questions about this one? I think I've got at least one more in here. All right, so this is not the exact same picture, but it's the same idea. You'll notice when we did that last problem that my normal force was not equal to Fg. And that's because we had a third vertical force. We have Fg, we have Fn, but we also have a component of our diagonal tension force. And we had it in the last question too. So if the free body diagram represents a kid pulling a box of toys or the man pulling the crate from the previous question, how does the normal force compare to when it's not being pulled? Well, when he's pulling at an angle like this, normal force is going to be smaller than Fg, and you can see it there. And we can see it in our calculation here. Fg was 304, normal force was only 192. Okay, and the reason for that is because there is that third vertical force. Ft plus Fn have to equal Fg. Okay, so just a heads up, if he were to stop pulling entirely, drop the rope, then Fn and Fg would be equal because the crate's still not going to be accelerating vertically. It's just going to be sitting on the ground. All right, so just something to keep in mind. Don't assume that Fn equals Fg. It is usually true unless you're pulling something at an angle or pushing something at an angle. Upward forces on an object that sits on or moves along a surface result in a smaller normal force from the surface. Again, if you're pulling up at an angle, this is going to be true. It's what we just looked at. All right, so here's the problem that goes with that picture. It says, Tom pulls a 12 kilogram toy box with a force of 59.5 newtons at an angle of 36 degrees above the ground. The coefficient of friction is 0.27. So I wasn't as nice with this one. I didn't give you the force of friction. I gave you the coefficient, which means we're going to have to calculate the force of friction at some point because it's part of our net force, and we're going to need that in order to get acceleration. Okay, so same process. If you have a force at an angle, get the components. Okay, Ft in the y direction is going to end up being 59.5 times sine of 36. I didn't even put the math up here, but that's what it is. It's going to be 59.5 times sine 36, and I'm using sine because this is opposite. And when I do, I get that, 34.9732. Again, I probably rounded that. I don't remember. Similarly, we're going to find this horizontal component. We're going to use cosine because it's adjacent to our angle, which means we're going to be doing 59.5 times cosine of 36 degrees, which is 48.1365 newtons. So now we have the components. Again, that's step one. If you have a force at an angle, get those pieces so that you can draw them on your free body diagram. We're also going to need to include friction. Okay, I don't know what friction is yet, and I can't calculate it just yet, but I'm going to draw it right here for now. We have Fg. I could find that because I know Fg is mg, and I know the mass is 12. It's in the question. Okay, and then we, of course, have Fn, but I'm going to draw Fn shorter than Fg. We just talked about this a second ago. Fn and Ft are both up. Together, they have to equal Fg. Okay, so when I draw it, I'll draw it shorter. I don't know how short exactly, but shorter than Fg to remind myself later on. All right, again, forces up have to equal forces down because this crate is not accelerating vertically. So again, I know Ft plus Fn will equal Fg. Okay, and here's how my free body diagram, would look if I wasn't doing it on top of the picture. Okay, like this one over here. So from here, let's get rid of the picture. We can solve Fg. Let's go ahead and get some numbers onto this diagram. Again, Fg is mass times gravitational acceleration. That's 12 times negative 9.8, which is going to give us negative 117.6 newtons. It's downward, that's why it's negative. So when you label it here, you don't have to put the negative sign, but this is going to be 117.6 down. Again, if my vertical forces are balanced, then Fn plus the vertical component, which was 34.973, or I have it as 35 right here. Those two together have to equal 117.6. They're equal in magnitude.
I don't see that in my...
That's why you need to turn the animations on. Okay, that is why I have absolute value signs there. Okay, because it's not negative 117. Click the arrow.
Okay.
All right. So that means if I subtract 34.973 from 117.6, I get 82.627 newtons. Double check and make sure. These two should add up to 117.6, and they do. Okay, and so there's Fn, there's my other vertical component of tension, and then they should together equal Fg, which is 117.6. All right, so again, we have found the numbers for everything except Ff. Ff, though, we have an equation for that. Force of friction is mu times Fn. We just found Fn, 82.627. Mu is in the question, 0.27. So we just multiply those together, 0.27 times 82.627, and we get a force of friction. It's to the left, so it's negative, of negative 22.31 newtons. Again, you can find all the pieces. And usually you have to find all the pieces so that you can solve the rest of the problem. All right, so I have labeled my picture with all of my numbers. From here, now we can find acceleration because I can look at this diagram now and I can get net force. F net y is 0. Again, we drew it like that on purpose. All vertical force is balanced. There's no vertical acceleration. But F net x is the sum of my horizontal forces, and I have two. The yellow one, which is the horizontal component of my tension, and the gray one for friction. When we add them, though, make sure you put that negative sign in front of friction. And so now I have 48.1365, that's this yellow one right here, plus negative 22.31, or if I unround it, negative 22.3092. Okay, and when I add those together, really I'm subtracting, I'm going to get 25.83 newtons to the right. Again, we're not done. That's just the net force. We now use that net force along with the mass from the question to find acceleration. But before I do that, does anybody have a question about how we got this far?
So, ma'am, quick question.
Is it about this?
No.
Okay, then ask me later. All right. So my total net force is 25.83 newtons to the right. All right, with that, we can find acceleration. F net equals ma, we have F net, we have m. 25.83 equals 12 times a, divide both sides by 12, and our acceleration ends up being 2.15 meters per second squared to the right. Again, a lot of work just to answer one question. So these types of things with this many steps, probably not going to show up on a multiple choice test question. It's a lot of steps. It would, however, potentially show up on a free response because we could check each of those steps. Okay, and so that's where you could get partial credit for stuff like that. Y'all had one on the last test. Y'all actually did really good on the free response. The math on the last test was probably the part y'all did the best on. Okay, was those multi-step problems. So we're getting the hang of it, but they are lengthy. All right, here's a follow-up question. It says, same thing, but it says, if it starts from rest, what is its change in momentum if it's pulled for 2 seconds? And I accidentally didn't turn my animations on, but that's okay. Change in momentum is mass times change in velocity, which means final velocity minus initial velocity. So mass times this. Okay, the problem is I don't have a final velocity. So here's where we're going to be going with these. And I'm just going to do this one today. But tomorrow you're going to have even more kinematic equations brought in. Okay, but I have VF equals VI plus A times T, which means VF equals 0. That's VI. It says it starts from rest. Plus A, that's the acceleration we found just a moment ago, 2.15, times the time from the question, 2. And 2.15 times 2 is 4.3. And so the final velocity is positive 4.3 meters per second. And so if I want to find my change in momentum, I just do my mass, 12, times my change in velocity, which would be 4.3 minus 0, since it started from rest. So 12 times 4.3 is positive 51.6 kilogram meters per second. So all these things we've been doing are all going to come together in some of these calculations, like this, where you have to use kinematics to get a velocity and then maybe change in momentum after that. Most of your problems today, in fact, I don't think any of your problems today have this in it yet, because this is in tomorrow's notes. But I just wanted to show you kind of where we're going. I have them animated here. Here's all our givens. I just forgot to turn it on for the other part. Okay, so we used that when we plugged in here. All right, guys, for the rest of the class period today, you are working on 301.2. That is the problem set that you started on Friday. Maybe you already finished it. I don't know. But if not, then you can work on it for the rest of the period today. It is due by 11:59 p.m. tonight. You also have a forces RA that is due tomorrow. Now, I do want to say something about the forces RA because Mr. Quigley put that together and he sent a message this morning to myself and Ms. Begg. Y'all might want to hear this, that there is a typo in the code that he has that's scoring it for you. I think he said it's deducting like 15 points. So I don't know that it's possible for you to get over an 85 on it. We are going to fix it. I just have to go in and open up every single person's document individually to fix it. But just a heads up, if you're sitting at an 85, you probably actually have full credit. Again, I have to go in and paste that into your cell. So I'm going to be doing that today, tomorrow, this week, just to make sure everybody has the right scores. But just a heads up on that. The forces RA, if you're sitting at an 85, that's probably full credit. Again, I don't know without actually fixing the code. The other thing I want to remind you of, the optional rocket bonus project, if you're doing it, it is due next week. You are running out of time. You don't have to do it. It is completely optional. But if you want to do it, remember it replaces a test, not just up to a 70, up to a 100. So if your last test didn't go so well, I would still recommend you retest because we have one more test, Unit 3, and you might end up needing the project for that. Okay, we don't know. So I would encourage you to retest if you need to on the Unit 2 test. The rocket project could then either replace that retest grade or Unit 3, whichever is lower. Okay, but that is due by the 8th. That is next week at 3 p.m. All right, guys, go ahead and get to work. If you have any questions as you're working, please let me know. I strongly encourage you to keep out paper, to draw those free body diagrams, and to show your work as you are working through these problems today.